Now let's move on to the next law right here, the second law. Okay, for the second law I need you to understand something called momentum. Okay, we have studied or we have talked about inertia. Inertia is essentially something that that talks about the mass. Okay, but we also need something that requires to talk about both the mass as well as velocity, because momentum is that particular quantity which is essentially the multiplication of, or it's mass times velocity, right? So something that that has a very high momentum would essentially have a product mass into velocity which is much greater, right? So mass into velocity is the momentum. Its unit is kg meter per second. Okay, its unit is kg meter per second. Now what does second law entail? Well, Newton said that the rate of change of momentum is force. Yeah, he defined force in the second law, guys. He said the rate of change of momentum is force. And you know what, we generally use the dumbed down version of the Newton's second law, but I'm gonna explain a little bit on what the actual law is. He said the force is directly proportional to change of momentum with respect to time. Now this is, I'm involving differential calculus here. I hope you know this already. If you don't, then go back to my lectures on calculus. You need the calculus to be able to understand this one. Now Newton said force is directly proportional to momentum, rate of change of momentum. Well, momentum is mass into velocity, so I'm gonna say force is directly proportional to mass into velocity with respect to time. You differentiate mass into velocity with respect to time, but this proportionality constant is equals to 1. So now you just differentiate mass into velocity, considering mass to be constant. If you differentiate this, mass comes out. But what if you don't assume anything and just differentiate? Well, you remember the product rule. You're gonna say something like this: mass into differentiation of velocity with respect to time plus velocity into differentiation of mass with respect to time. Now this is something called the product rule in differentiation. If you haven't done this already, please refer to my lectures on basic introductory calculus before physics. Okay, so never mind, let's continue with this. Now here we see two terms here, right? This is term number 1, which I'm going to talk about here, and then I want to talk about this particular term when we are here. Okay, so let's quickly do this. Okay, where's my pen? Yes, now let's talk about this. M into dv by dt. What is dv by dt? What is the rate of change of velocity with respect to time? This is nothing but mass into acceleration. This is the generally dumbed down version of F equals to or Newton's second law that we know. We pretty much say, if someone asks us what is Newton's second law, there's a tendency you're gonna say it's mass into acceleration, but it's not. It's only half of the equation, because the other part is v into dm by dt. This is known as thrust, and this is what pushes our rockets in the forward direction, right? This is what pushes the rocket in the forward direction. Now when the rockets fly in the space, okay, when rockets fly in the space, 1 second, yeah, they use something called thrust. Now what exactly is thrust? Well, the rockets, they burn the fuel at a very high speed, so its mass continuously decreases. So force equation as a whole is not just mass into dv by dt or mass into acceleration. It's mass into acceleration plus v into dm by dt. Now we know that rocket does not have anything physical to push it upwards, but it does have fuel that it can burn at a very high rate, creating a mass rate. Now what is dm by dt? Please understand, is the rate at which the mass is increasing or decreasing. Any change in mass at a constant velocity is also going to create force. This is how rockets push themselves into the space. They burn their fuel at a very high rate, creating a thrust. And also all the jet engines, to be honest, all the fighter jets, they burn the fuel at a very high rate, creating a force, right? So this component of the force is also known as thrust that is generated. Okay, thrust. Now most of the cases, like the 70% cases in the classical physics that you're gonna deal with, is gonna have mass constant. Like when I say a block is there and you apply 10 Newton force on a 5 kg block, Most of the time the acceleration simply comes out to be 10 by 5, which is 2 meter per second square. Now this is just F equals to ma, so you don't have to worry about the thrust part for most part of the calculus. 90% of the classical mechanics that you're gonna study in your 11th standard will not involve this formula. Occasionally in your modules, in your standard textbook, sometimes you might get a situation where you have this particular component of force as well. Now let's focus down on F equals to ma. Just like first law, this is valid not just in one direction but in all the separate directions. Like if you want to find out the forces along x, you could do m into ax. Forces along y, and please don't forget to give this arrow sign on top, implying that these are vector quantities, right? So these are vector quantities. Fy is equals to nothing but m into ay, and fz is nothing but m into az. Now this is again the application. This is essentially the second law, which is given to us by very great Mr. Isaac Newton. Okay. Now imagine you have a cylinder like this. Okay, you have a cylinder like this, right? And it's kept on the floor. Like this. Okay. Now if you apply a force exactly damn at the center of the cylinder, it's gonna just slide like this. It's gonna slide along the floor like this. Okay. But imagine you applied a force on top, and a very huge force on top. There are chances that this thing can go boop. I hope you understand. Okay, so that is where point mass assumption comes into play, right? If you have a point mass assumption, essentially it means ki if you have a body like this and you say it's a point mass, it doesn't really matter if you apply the force here, right? You are pretty much assuming ki these dimensions are meaningless. These are very small, so as to so that I can consider it to be like a small point mass. Yeah, so in the point mass assumption, we disregard the dimensions of the body, and we consider it to be very small, so as to mimic a point mass. Now in the point mass, the only thing we need to worry about is the force, the linear force, right? We don't have to worry about whether it's creating any sort of rotation or not. So that is point mass assumption. That is always valid in case of Newton's second law and the first law and all the three laws actually, right? Now that is something that I wanted to talk about. Now the third law is something very favorite to students. Okay, they like to say that every force has an equal and opposite reaction. Okay, opposite reaction. Now the action reaction pair acts on two different bodies. Guys, this is one statement that I need you to understand, because everyone kind of remembers the first one, the second one being also very important for the application part of it. The action reaction pair acts on two different bodies, guys, two different bodies. Now what are action reaction pairs? Like I was talking about ki if you essentially apply a force by your hand, I'm gonna try to make a hand. Oops, I don't know if that is the correct way to make a hand, but if you apply if you have a hand and you apply a force on this block, okay, you apply a force on this block and the block moves. So when I make your FBD, when I make your hands FBD, so the force that the block will be applying on your hand is going to be, let's say, F, and the force that you apply on this block is also going to be the same one but in the opposite direction. Okay, this is what Newton's third law says. Anytime there is going to be an interaction between two bodies, if body A applies F force on body B, then B applies the same amount of force on A, and that is the end of it. That's the third law. Now sometimes people think sir, the net force in that case is always zero. No, see, when we say the net force, you should also associate like net force on what exactly? Are you saying the net force on the block is 0? The answer would be no. On the block there is an external force, that F you're applying, right? But when you consider the hand and the block to be one complete system, then yeah, the net forces on that system as a whole would be 0. Your hand, if you consider as a system, then there is an external force. If you consider the block to be a system, then the block also has an external force. But the combined system does not have a net external force. Some applications of these would be something like the recoil that gunman feels. Okay, now look at this animation, or I would say the GIF here. So as the bullet leaves, there's a tremendous amount of force that the bullet applies on the gun as well. That's the reason for recoil. Okay, so when the gun fires, this is a perfect example of the recoil, and the recoil is a perfect example of the third law in action right there. Okay, so the bullet applies, the gun applies a huge force on the bullet, which pushes it forward, and in the same way the bullet also applies a huge amount of force on the gun itself. Okay, now I have one more example. I think I had it somewhere. Okay, one question I had for you guys is this one. What exactly, how will you explain this particular scenario? With what law will you explain this particular scenario? Have a go at it. Think on which law is this properly validating. This is essentially Newton's first law in action, right? Now when the car is moving at very high speeds, your body is also moving with it. As soon as your car hits something, your body keeps keeps tending to move with the same velocity, and that is the reason these dummies, they are just pushed forward. It's because suddenly the body has come to rest, but the dummies don't want to come to rest. They just want to travel at 100 kilometers per hour, right? So that property itself is known as inertia. It comes by mass. So a higher body or a heavier body will take much more damage than a lighter body in a crash like this, because the inertia component is directly proportional to mass. More the mass, higher is the inertia. So that's the end of all the three laws that I wanted to talk about. Now let's see the application part of it, guys. Let's see the application part of it.